Let's be honest, we are drowning in data. But most of it, it's just a chaotic mess of noise. What if I told you there's a way to see right through that chaos? Well, in this explainer, we're going to dive into a powerful framework that does exactly that. It finds the true, hidden reality buried under all that noise.
This right here, this is the fundamental challenge, isn't it? I mean, whether you're an economist, an engineer, or really just anyone trying to make sense of the world, you're always up against this problem. How do you separate the real, meaningful pattern from all the random static?
You see it all the time with economic data. A quarterly GDP report comes out and it spikes, or maybe it dips. But was that just a one-time thing? What's the real trend of the economy? That's the signal, the true story we're trying to find, and it's buried in those messy reports.
And this gets to the heart of the problem. On one hand, you have the observed measurement. That's the messy, fluctuating data we can actually get our hands on. And on the other, you have the unobserved state. That's the true, clean reality we really want to know. The whole game is about bridging that gap.
So how do we bridge it? You can't just guess. You need a specific language, a way of thinking designed for this exact problem. And that's where something called the state space framework comes in.
To really get our heads around this, let's use a simple story. Imagine you're trying to track a hiker deep in a forest. You can't see them directly. Their actual, true position, that's the hidden state. All you have is the GPS ping you get on your phone, which, as we all know, is never perfect. It's always a little bit off, a little bit noisy.
Okay, this image right here lays it all out perfectly. Think of it as two layers. Down below, you have the unobserved state. That's the hiker's actual path as they move through the forest. Then, on the top layer, you have the observed data. That's the stream of noisy GPS pings that are caused by their movement. Our model needs to connect these two layers.
So first up is what's called the state equation. It sounds technical, but it's just our model for how the hidden thing is changing. For our hiker, this is our theory about how they walk. We might assume they walk at a pretty steady pace, but maybe they wander a bit. This equation describes the evolution of the part we can't see.
Then, second, you have the measurement equation. This is the crucial link. It connects that hidden state to the data we can actually see. It basically asks, okay, if the hiker is really at this specific spot, what kind of GPS signal should I expect to get? This part is what accounts for all the noise and error from our GPS.
Now, here's a key detail that makes this whole approach so incredibly powerful. It's an idea called a Markov process. And put simply, it means the system is memoryless. To predict where our hiker is right now, we only need to know where they were a second ago. We don't need their entire path history. And that right there makes the math unbelievably fast and efficient.
Okay, so we've got the framework. We know how to describe the problem. But how do we actually solve the puzzle and figure out where the hiker is? Well, for a huge range of these problems, the answer is an absolutely brilliant algorithm called the Kalman filter.
Meet the star of the show. The Kalman filter has an amazing history. It was developed to help track spacecraft for the Apollo missions. It works its magic in situations where things evolve in a relatively predictable way, that's the linear part, and where the noise is random but generally clusters around the true value, kind of like a bell curve. And the filter itself? It's just a simple repeating loop. And here are the steps in that loop. It's this beautiful three-step dance. First, you predict. Based on your last best guess, you predict where the hiker is now. Second, you measure. A new, noisy GPS ping comes in. And third, this is the magic, you update. You intelligently combine your prediction and that new measurement to get an even better estimate of where the hiker really is, and you just do that again and again and again.
So what's actually happening in that update step? Well, at its core, it's a really smart weighted average. The filter calculates this thing, sometimes called the Kalman gain. That's basically a trust dial. It decides how much to trust the new GPS ping versus its own prediction. If the GPS is super noisy and unreliable, it'll trust its prediction more. But if its own prediction is a bit shaky, it'll listen more to the new data. It's a constant, brilliant balancing act.
So tracking hikers and spacecraft is pretty cool, but this whole idea is so much bigger than that. The real power here is its almost shocking versatility. You can apply this framework to a mind-blowing range of problems in all sorts of different fields.
In finance, for instance, it's the engine behind some seriously complex models for stock prices, things with those intimidating names like ARMA and GARCH. It can even handle situations where your inputs themselves are flawed. And get this,
It can estimate totally abstract concepts, like trying to figure out what people expect the real interest rate to be. You can't measure that directly, but the filter can estimate it.
But one of its most amazing tricks is how it deals with missing data. So what if our hiker's GPS cuts out for a few minutes? The Kalman filter doesn't panic. It just keeps running its predict step over and over, essentially coasting on its own internal model. It gives you the best possible guess until a new measurement finally arrives. It's just an incredibly elegant solution.
Okay, let's just quickly touch on a slightly more advanced point. Everything we've talked about so far is the Kalman filter, and it gives you the best possible estimate of the present moment. But what if you have all the data collected and you want to go back and get the absolute best estimate for something that happened in the past? For that, you use a Kalman smoother. It runs the filter all the way to the end, then works backward, using the benefit of hindsight to clean up all the past estimates. So, let's zoom out here. What is the big, powerful idea you should really take away from all this?
It really comes down to this. State space models give us a formal language to describe systems where the thing we truly care about is hidden from view. And the Kalman filter, that's the practical, efficient, beautiful tool that lets us actually peer through all the noise and reveal that hidden reality.
And let's not forget how incredibly efficient this all is. Remember that memoryless property we talked about? It means the filter only needs to remember the single most recent estimate to figure out the next one. It doesn't have to reprocess the entire history of data every single time. That's why this isn't just for supercomputers. It's running in real time right now on your phone's GPS.
And that leaves us with one last thought. Once you have this mental model, you honestly start seeing it everywhere. From the true state of a patient's health that's hidden behind a few lab tests to the true public opinion hidden behind a noisy political poll. So the real question is, what hidden systems are all around you, just waiting for the right model to bring them into the light?